Welcome to the Denver Metroplex Community Engagement video series. This presentation will provide a basic explanation of how the Federal Aviation Administration's air traffic control system works. The most important responsibilities of an air traffic controller are to ensure airplanes are safely separated from each other while maintaining the most efficient flow of air traffic. Accomplishing this is complex and labor-intensive. Air traffic controllers have to keep aircraft properly separated as they move through the system. In a busy airspace like Denver, a single controller is responsible for simultaneously directing aircraft for Denver International and multiple busy general aviation airports. Wind direction and velocity determine departure and landing direction. Aircraft generally must take off and land into the wind. Denver airports experience variable and strong winds, with the airport operating pattern changing to match the winds. One typical flow is north flow when the wind is from the north. At Denver International, the airport is typically in north flow where aircraft take off to the north, east, and west. For arriving aircraft, air traffic control manages arrivals from all directions, sequenced to land on up to 3 runways simultaneously. Aircraft are sequenced and merged into each arrival stream, landing to the north. The departures and arrivals have numerous crossing routes where the departures must be separated from arrivals. Controllers continuously manage and separate arrivals and departures simultaneously throughout the day. Adding to this complexity in Denver are the numerous aircraft operating at multiple surrounding airports in this crowded airspace. Aircraft flying at the same altitude must remain a minimum lateral distance from each other. In airspace surrounding airports, the minimum lateral distance is 3 miles. In higher altitude airspace, the minimum lateral distance is 5 miles. If aircraft don't meet the lateral distance separation requirements, they must remain a minimum vertical distance from each other. In normal flight altitudes for commercial aircraft, the minimum vertical distance is 1,000 feet. Conventional procedures utilize ground-based navigational aids, or nav aids. This picture shows a nav aid. We first started using nav aids in the 1940s, and the basic operational concept has remained unchanged since then. These decades-old radio beacons are used to direct aircraft along routes that require them to fly from point to point and provide information to the pilot as to the aircraft's position. All over the country, we are replacing old routes that use nav aids with new routes that rely on global positioning satellites, or GPS. The accuracy of GPS allows us to develop more precise routes that provide separation from one another. The revolutions in navigation and sharing of data have changed the way you conduct daily life. Just as the internet has altered how we communicate, new technologies have transformed the way we fly airplanes. Airports that make up our transportation system don't look much different than they have in the past decade or two. The way in which aircraft are guided and controlled are changing significantly. Satellite navigation and new ways in sharing data are creating benefits in improving safety and efficiency of aircraft operations in the national airspace. Satellite-based routes aren't just making today's system safer and more efficient. They're also laying the foundation for further improvements to safety and efficiency. One example is time-based metering. This system allows us to precisely meter the flow of aircraft to and from airports by knowing with greater predictability where an aircraft will be at a specific time. Time-based metering is key to the evolution of our air traffic control system and was part of the initial next-gen implementation in Denver. We call this modernization of our airspace system the Next Generation Air Transportation System, or NextGen. Satellite-based procedures are a significant element of time-based metering. As we move towards time-based operations, we will be able to tell where each aircraft will be at any point in time along the way to its destination. This will be an additional enhancement to our ability to manage air traffic more safely and efficiently. A traditional descent is like walking down a flight of stairs. Based on air traffic controller instructions, the pilot descends and applies speed brakes, then levels off and powers up the engines, then descends and applies speed brakes again. The cycle repeats itself until the plane is on final approach to an airport. By contrast, an optimized profile descent, or OPD, has built-in speed and altitude requirements at various points on the route. This information is programmed into the airplane's flight computers and allows them to essentially glide down to an airport on idle power and controllers don't have to issue instructions after clearing the plane to begin its descent. An OPD and optimized climb profile are much more efficient than traditional descents and climbs, and the key benefits that we're seeing today from our use of satellite-based procedures. OPDs are safer in that there is less pilot-controller interaction. Airplanes flying OPDs versus a traditional descent generate less noise and emit less pollution because their engines are near idle and speed brake use is minimized. An optimized climb profile is like the reverse of an OPD. It allows a plane to climb unrestricted to its cruising altitude, separated from crossing traffic. Denver Metroplex airports have routes that weave under, over, and around each other. High traffic volume, mountainous terrain, and challenging weather were factors taken into consideration with the new Metroplex routes. This video provides a basic understanding of how the air traffic control system works, how the FAA is modernizing through NextGen, and why it is necessary. For more information and additional animations on the Denver Metroplex, please visit our website.